So last time we worked with, on this example here, we derived this relationship for Compton scattering, which is to say that light is a particle made of photons to double check or confirm the photoelectric effect conclusions. So we have a photon here that is incident with some wavelength lambda. There is an electron that is not moving. They collide. The photon takes this direction and the electron takes this other direction. And the relationship between the wavelengths and this angle and the mass of the electron and this h here is what? What is this? H?
Planck's constant.
Planck's constant. Good. It has some numerical value. So we got this relationship, we derived it. You can refer to that later. Let's say we're doing this experiment. We use X-rays, so the wavelength is 0.124 nanometers. So that's in the X-ray range. And in a Compton scattering experiment, so we use X-rays of this wavelength in a Compton scattering experiment. And at what angle is the wavelength of the scattered X-rays 1% longer than the incident X-rays? At what angle are the scattered X-rays longer by 1%? Okay? So it's a direct application of this. So what does it mean? Means lambda prime is equal to lambda plus 1% of lambda, right? Just to translate it in words, right? So that means lambda prime minus lambda is 1% of lambda, which is to say 1% is 0.01 times the original wavelength, which is 0.124 nanometers. Let's convert everything this to meters, so I get 10 to the minus 2 times 1.24 times 10 to the minus 10 meters, and that is 1.24 times 10 to the minus 12 meters. Yes? That would be the lambda minus lambda prime. Sounds good. Now, to find the angle, we just have to solve for the angle. Thank you. So we get phi is equal to, will be cosine inverse of, let's try to do this in one shot. So we get, have to multiply and then do 1 minus mc over h times lambda prime minus lambda. So, do you agree with that? Yeah, I think that's right. And all we have to do is plug in the numbers now. So you have the mass, it's an electron, so speed of light. Lambda. Oh, why not lambda? You see, over h, right? Not lambda here. It should say h. 6 minus 6 minus 34. And then lambda minus lambda prime, or lambda prime minus lambda is 1.24. Okay. So doing that, you get 60.7. 60.7. It's an angle in degrees. would be the angle. Okay. Now, the next topic would be pair production or pair annihilation. Before I discuss that one, I would like to calculate how much energy is in these X-ray photons. How much energy do they have? Okay. And I will change that to, I will write that energy in electron volts. And then compare it to the energy of the rest energy of an electron or a proton. Okay. So sounds good. So what is the energy of an X-ray? The energy of an X-ray photon. Let's say that X-ray photon has this much. Is this wavelength. Remember, the energy for a photon is hc over lambda, right? It's hc over lambda. So let's calculate the energy. It will be 6.626 times 10 to the minus 34, 3 times 10 to the 8th divided by lambda, which is 1.24 times 10 to the minus 10 meters. Okay. So I need help with this one actually. I don't have the numbers. How many joules is this? Is it something times 10 to the minus 16? Actually, no, it should be 15 because 6 times 3 would be over 10. How much?
1.603.
1.603. I'll just use approximate. Thank you, though. Times 10 to the minus 15. 15 joules. The reason I like 1.6 because I want to convert this to electron volts. What do we do to convert to electron volts? We divide by 1.6 times 10 to the minus 19, right? And 1.6 over 1.6 become a 1. 10 to the minus 19 take it up becomes 10 to the plus 19. So this would be 10 to the 4 electron volts. So it will equal to this. 10 to the 4 EVs. And if I convert it to mega electron volts, it will be 0.01 MeVs. Okay? Let's find the rest mass of an electron and then the rest mass of a proton. Okay? Just as an exercise. Rest mass of a proton of an electron is m electron times c squared. The mass of an electron, technically to get the precise number, I need the precise mass of the electron. Instead of 9.11 times 10 to the minus 31, it's 9.108 or 09, I forgot. And the speed of light, you should use the actual speed of light instead of just exactly 3, it's 2.998. So let's use the almost close the speed of light, I think. So here you get 9.11 times 10 to the minus 31 kilograms. But for the speed of light, I will use 2.998 times 10 to the 8th. This will be in joules, squared. This will be in joules, right? I want it in electron volts, so I need to divide by what?
1.6.
1.602 times 10 to the minus 19. So, how many electron volts would this be? Should do it.
5.11 times 10 to the fifth.
To the fifth, yeah. So I would write it as 0.511 MeVs, mega electron volts. Okay. So notice an X-ray photon has nowhere near the energy needed to make an electron, right? Has nowhere near the energy, the rest energy of an electron. How about the proton? Well, it would be the mass of the proton times c squared. It would be even bigger. Mass of the proton is about 1.67 times 10 to the minus 27. And then the rest is going to be the same, times the speed of light squared. Divided by, because I want electron volts, and then we change it to MeVs. We need to divide by the charge. I mean, the numerical value. 1.602 times 10 to the minus 19. So this is 1.602 times 10 to the minus 19 joules per electron volt. So the result will be in electron volts, but we want MeVs. Can someone tell me how many MeVs is it? Hey, it would be 930 something. I forgot the number. This is MeVs, so million, right? So
937.
937? Okay. 937. I believe it's closer.
96.9.
Oh, 936. I believe it's closer to 938 if you use the exact numbers. Okay. Anyways, around 940. Okay, around 940 MeVs. So for pair production, what happens is this. Let's just recap. When we talked about the photoelectric effect, the photon was completely absorbed by the electron, and then the electron was freed, right, from the surface of that metal. For Compton scattering, the photon collides with an electron. The photon goes one angle, and the electron goes to the other angle. For pair production, what happens is let's say you have a target here, some mass M, and your photon comes in, it hits this mass M, and then after the mass may recoil, it might recoil and have some speed this way, and then maybe an electron is produced, maybe it moves in a certain direction, and a positron, so let's say this is a positron, and this one is the electron. Notice they have opposite charges, so the charge is conserved. If you didn't have any charge before collision, the net charge after collision is still zero. But what happens is the photon disappears and these two appear. Okay? So the photon energy, to conserve energy, let's say the motion of this is negligible, right? Let's say the motion of this is negligible. Then this mass is this mass, that's accounted for. And let's say its kinetic energy is negligible. So the new things that came out is the electron and the positron. Even if they're at rest, the photon needs to have at least the rest energy of the electron plus the rest energy of the positron, probably some more. This one will be moving, okay? And chances are they will be moving also. So you will have the photon, right? This is an electron. Positron has the same rest energy. So the the photon that you need must have an energy of at least one, or a little more than 1 mega electron volts, 1 MeV. Now, an X-ray doesn't have that, it's 0.01, so you need gamma rays. Gamma rays are the highest frequency or the most energetic of all the, in the range of the spectrum. They have the most energy. Okay? That's pair production. And then there is the reverse of pair production. I could not spell this word. Yeah. Pair annihilation. Is it an E or an I? All of them are I's, okay? Okay, good. What happens there? It's basically the reverse process, the reverse of this process. What happens is you have a pair, let's say an electron, a positron. They collide with one another, right? They collide with one another, and then they just destroy one another. They disappear, and what appears is, this is after. What appears is a pair of photons. Let me ask you the following question. Let's say this electron had speed v, or velocity v to the right, and this positron has velocity v to the left. They collide. They disappear. A photon pops up. Can that be the case? Can you just have one photon come up?
No.
No, why not?
Charge.
It will, well, the total charge before is 0 and total charge after is 0, so that's fine. The mass, if enough energy in that photon, we can account for the mass energy.
It's the momentum.
The momentum. What's the total momentum before collision here?
0.
0, right? One of them move into the left, one move into the right. So if I just produce one photon, a photon can't be at rest. We'll be moving at the speed of light. It would have some momentum in that direction. Well, I need another photon to go with it, but it has to go in the opposite direction. That way, you will account for the momentum. So you need to conserve a bunch of things at the same time: the charge, energy, and momentum. And there are other things also that need to be conserved. So that's this one. Let's do we'll do an example on this. And then what's all this about? Why are these experiments done, and what do they tell us? Conservation laws, okay. And there is one more. That there are photons, they're particles. That's the point. So an electron, positron, initially far away, and they move towards each other with the same speed. So here is an electron, positron, same speed. And what happens, they collide, and then they destroy one another, and then they disappear. So this is before. So this is before. And then afterwards, you get two photons. And the question is, what are the energies and the wavelengths and the frequencies of the photons? Okay. So let's do it so our goal is to find lambda, the energy, let's write it this way, the energy, lambda, and the frequency of the photons. So this is before, this is after. Is the picture clear what I'm trying to say? Okay. But I need to tell you more. I need to tell you either the velocities of those photons, or I'm sorry, of the electron positron, or how much energy they had in total, or something like that, right? Let's say they're kinetic. Let's do it for this case. Assume V is basically 0. Let's assume their velocities are 0. So we will use conservation of energy, right? So conservation of energy says what? The kinetic energy before collision for the first electron plus its rest mass energy, mc squared, right? That's for the first electron. For the electron, the positron will have the same speed, so same thing, right? Twice, huh? Yeah. So you get 2, right? And then I will, if the kinetic energy is, if V is about 0, this will be 0. I'm just doing it in general, and then we do it specifically for this. And this must equal to the 2 energies of the photons. So 2 energy of photon 1 plus energy of photon 2. So that's twice the energy. Okay. So the number 2 cancels, and we get the energy of each photon, which is K plus mc squared. So if so this is, I should have written this above. Yeah, I should have written it above because I'm doing part A. So if the kinetic energy is basically 0, then the energy would just be mc squared, and that is 0.511 MeV. Then what would the wavelength be? Or let's do the frequency first. The frequency, we know that the energy is what? H times the frequency, right? H times the frequency. So the frequency would be the energy divided by H. Energy divided by H. Let me look up H in terms of, because you can write H in EVs also. So here is H. So the energy is 0.511 MeVs. So it would be EVs times 10 to the 6th. So times 10 to the 6th EVs. And then H, it's 6.626 times 10 to the minus 34 joules times seconds. But in terms of EVs, here's H. It's 4.136 times 10 to the minus 15 EVs times second. Okay? Seconds. So EVs also. So this tells us that the frequency is 1.24 times 10 to the 20 hertz. 24 times 10 to the 20 hertz. Okay. And then the wavelength is speed of light over the frequency. And you just have to put the speed of light divided by the frequency. I will just skip that. I will just write it down. It's 2.43 times 10 to the minus 12 meters. Okay. That's their weight. So these are gamma rays. Okay? And they have basically 100 times more energy or so, or more, or 1,000 times could be, or more than X-rays. They're much more energetic. So this is this. Any questions on what I've done? So next time we're going to start a newer topic. It would be, our next topic will be the wave-particle duality, and then we'll begin the next chapter also. Okay. So let me stop here.